Welcome to the quantum world. This isn't a place you can visit, but it's the realm that underpins everything that exists. It's a place where the familiar logic of our everyday lives shatters into a million pieces, and information itself behaves in ways that seem like magic. Here, particles can be in multiple places at once. They can be intrinsically linked across vast distances, communicating faster than the speed of light. They can exist in a ghostly fog of potential until the moment we decide to look at them. For decades, this world was the exclusive domain of theoretical physicists, a beautiful but untouchable mathematical landscape. But that is changing. We are now building machines that don't just study this world, but speak its language. These are quantum computers, and they harness the seemingly impossible principles of superposition and entanglement to solve problems so monstrously complex that they would take our fastest supercomputers billions of years to even attempt. Today, we are embarking on an extraordinary journey together. We will travel from the very heart of the quantum atom, the qubit, to the mind-bending algorithms that unlock its power. We'll explore the elegant hardware that tames this wild frontier, the clever techniques of error correction that keep it stable, and the real-world applications that are poised to reshape our future. And at the end of our journey, we'll discover how modern tools, like the collaborative AI system and GX Deep Research, are making this once impenetrable world accessible to us all. To understand the revolution, we must first understand the old world, the world of classical computing that powers our lives today. At the heart of your smartphone, your laptop, and the entire internet lies a simple, humble hero, the bit. Imagine a coin lying flat on a table. It can be heads or it can be tails. There is no in-between. It's a definite, unambiguous state. We label one 0 and the other 1. This binary certainty is the bedrock of all digital information. By stringing together billions of these tiny, decisive switches, we can build everything from a simple calculator to a sprawling virtual world. They are reliable, predictable, and incredibly powerful in their own right. But they have a fundamental limitation. They can only ever tell one part of the story at a time. A bit is a statement of fact. I am a 0 or I am a 1. Now, let's enter the quantum realm. Here, we meet the bit's enigmatic cousin, the qubit. Instead of a coin lying flat, imagine we spin it on the table. While it's spinning, is it heads or tails? The answer is ... yes. It's in a state of both and neither. It's a mesmerizing blur of potential, a perfect blend of the probability of being heads and the probability of being tails. This shimmering, uncertain state is what physicists call superposition. A qubit isn't a fixed statement of fact, it's a spectrum of possibility. It holds the potential for being a 0 and the potential for being a 1 all at the same time in a delicate, probabilistic dance. It only chooses a side when we force the issue, when we stop the coin and look. This act of looking is called a measurement. The moment we measure it, the superposition collapses and the qubit resolves into a definite classical state, a 0 or a 1. This might seem like a small difference, a definite state versus a potential one, but this single distinction is the crack in the foundation of classical computing through which an entirely new universe of computational power floods in. Classical bits build walls of certainty, one brick at a time. Qubits, on the other hand, explore a vast landscape of possibilities all at once. So a qubit can be a 0 and a 1 at the same time. Why is that such a monumental leap? Let's go back to our classical computer. Imagine it's trying to solve a complex maze. It has a single explorer, a classical bit. This explorer goes down one path. If it hits a dead end, it has to backtrack all the way to the beginning and try another path. It explores the maze sequentially, one possibility at a time. For a simple maze, this works fine. But for a maze with billions of possible paths, like factoring a massive number or designing a new drug molecule, this one-by-one approach becomes impossibly slow. Now imagine the quantum computer's approach. Thanks to superposition, it doesn't send one explorer into the maze. It sends in a qubit that exists in a superposition of all possible paths simultaneously. In a sense, it explores every single hallway, every turn, and every dead end at the very same time. It's not just faster, it's a fundamentally different way of processing reality. It's like being able to live out every possible choice you could make in a day, all at once, and then picking the outcome you want. The real magic, the source of its exponential power, happens when you add more qubits. If you have one classical bit, you have two possible states, 0 or 1. If you have two bits, you have four possible configurations, 00, 01, 10, or 11. But a classical computer can only represent one of these four configurations at any given moment. With quantum computers, every qubit you add doubles the number of possibilities it can explore simultaneously. One qubit can explore two states at once. 2 qubits can explore 4 states at once. 3 qubits can explore 8 states at once. 10 qubits explore 1024 states. 30 qubits explore over a billion states. By the time you get to just 300 qubits, the number of states it can hold in superposition is a number so titanically large it is greater than the estimated number of atoms in the entire observable universe. Think about that. A small device with just a few hundred atoms worth of quantum processors can simultaneously process a volume of information larger than the physical cosmos itself. This isn't just an upgrade, it is like graduating from a single-lane dirt road to an infinite-lane superhighway where every destination is reachable at the same time. This is the heart of quantum supremacy, the ability to command an exponentially growing computational space that classical machines can never, ever hope to touch. Let's deepen this comparison to truly appreciate the chasm between these two worlds. Imagine you're trying to describe a complex scene, like a bustling city square, using light switches. A classical system of, say, 8 bits is like having a row of 8 light switches. At any single moment, you can only represent one pattern. Maybe it's on off dash off dash on dash on dash off dash on dash off. This single pattern could represent a letter, a number, or a pixel color. To show another pattern, you have to flip the switches, erasing the first one. Your system can only hold one piece of the puzzle at a time. It's like a soloist playing one note, then the next, building a melody over time. Now picture a quantum system with 8 qubits. Thanks to superposition, this isn't a row of switches. It's a single, rich, holistic quantum state. Within this one state, all 256 possible combinations of those 8 qubits exist simultaneously. It's not just one pattern. It's 0000 living alongside 00001, 00010, and every other possibility, all the way to 11,111,111. This multi-qubit system isn't a soloist playing one note at a time. It's an entire symphony orchestra playing a massive, complex chord. Every possible harmony, every note, every instrument is present at once in a single, unified wave of information. The computation doesn't happen by changing the notes one by one. It happens by subtly changing the shape of the entire chord, guiding this symphony of possibilities toward a final, harmonious resolution. This is why we say that in qubits unlock to end quantum states working in parallel. It's not just about speed. It's about computational richness and density. A classical computer manipulates data. A quantum computer manipulates a universe of possibilities. This parallel existence allows a quantum computer to see the entire problem, the entire city square, at a glance, recognizing patterns and correlations that a classical computer looking at one tiny piece at a time would never be able to find. If superposition is the ability of one qubit to be in many states at once, then entanglement is the mysterious, almost telepathic connection that can exist between multiple qubits. Albert Einstein famously called it spooky action at a distance, and for good reason. It's one of the most profound and non-intuitive principles in all of science. Imagine you have 2 of our special quantum coins. We entangle them through a quantum process and then give one to you and one to a friend. Your friend travels to the other side of the galaxy. You both agree to spin your coins and measure them at the exact same time. You stop your coin, and it lands on heads. Instantly faster than the speed of light, with no signal or message sent between you, you know with 100% certainty that your friend's coin has landed on tails. If yours had landed on tails, you'd know theirs was heads. Before the measurement, both coins were in a superposition of heads and tails. But their fates were intertwined. They were no longer two independent coins. They were a single, unified system described by one quantum state. The state of one was perfectly anti-correlated with the state of the other, no matter how much space separated them. In a quantum computer, entanglement is not just a spooky curiosity, it is a critical resource. It is the quantum glue that allows qubits to coordinate their actions with a level of sophistication that classical bits could only dream of. When qubits are entangled, the information they hold is no longer just local to each qubit. It becomes a shared, global property of the entire system. A change to one entangled qubit can ripple through the others, allowing for complex, parallel computations where the qubits work together as a perfectly synchronized team. If superposition gives a quantum computer its vast computational space, entanglement provides the invisible threads that weave through that space, connecting different possibilities and allowing the computer to perform logical operations on a scale that would otherwise be impossible. It's the ultimate form of teamwork, amplifying the efficiency of quantum computation far beyond what superposition alone could achieve. We now have two of our three core ingredients: superposition, which creates a vast ocean of possibilities, and entanglement, which creates intricate, non-local connections within that ocean. But how do we navigate this ocean to find the one tiny island that holds the correct answer to our problem? This is where the third, and perhaps most crucial, principle comes into play: quantum interference. Just as waves of water can interact with each other, so too can the probability waves of a quantum system. When two wave crests meet, they combine to create a bigger wave. This is called constructive interference. When a crest meets a trough, they cancel each other out. This is destructive interference. A quantum algorithm is, at its core, a brilliantly choreographed dance of interference. The goal is to carefully manipulate the qubits in such a way that the probability waves corresponding to the wrong answers destructively interfere with each other, canceling themselves out into nothingness. At the same time, the waves corresponding to the correct answer are guided to constructively interfere, amplifying their probability until it's the most likely or only outcome when we finally make our measurement. Think of it like this: superposition throws millions of darts at a board all at once. Entanglement links the paths of these darts in complex ways, and interference acts like a set of precisely controlled wind currents that blow all the wrong darts off course while guiding the right one directly to the bullseye. The final measurement is like turning on the lights. When the quantum fog of superposition collapses, the landscape of probabilities has been reshaped by interference, and the answer we're looking for is standing there, clear as day. This powerful trio, superposition, entanglement, and interference, is the true engine of quantum performance. It's a method of computation that doesn't calculate an answer, but rather sculpts it out of the fabric of probability itself. All of this talk of probability, waves, and interference can feel incredibly abstract. How do scientists and engineers actually control and visualize this quantum ballet? They use two key tools: the block sphere and quantum gates. Don't be intimidated by the name. The block sphere is simply a beautiful and intuitive way to map the state of a single qubit. Imagine a globe. The North Pole represents the definite 1 state. The South Pole represents the definite 0 state. Any point on the surface of this globe represents a possible superposition. A point on the equator, for example, represents a perfect 50-50. It's mix of 0 and 1. A point closer to the North Pole represents a superposition that is more likely to collapse to a 1, and so on. The block sphere gives us a visual coordinate system for a qubit's potential. So if the block sphere is our map, how do we move the qubit state around on it? That's the job of quantum gates. Quantum gates are the fundamental operations of a quantum computer. They are the equivalent of the AND OR and NOT gates in classical computing, but they are far more sophisticated. Instead of flipping bits, they perform precise rotations on the block sphere. For example, an X gate is like a 180-degree rotation around the x-axis. It flips the state from the South Pole 0 to the North Pole 1, or vice versa. It's the quantum equivalent of a classical NOT gate. A Hadamard gate is one of the most important. It takes a qubit at the North or South Pole, a definite 0 or 1, and rotates it to a point on the equator, putting it into a perfect superposition. It's the gate that opens up the quantum possibilities. By stringing these gates together in a sequence, engineers create a quantum circuit. This circuit is the program. It is a set of instructions, a choreographed sequence of rotations and flips designed to guide the qubits through the complex dance of interference we talked about, steering them from an initial simple state to a final state that encodes the answer to our problem. These gates are the building blocks of every quantum algorithm, the tools we use to speak the language of the quantum world. This all sounds amazing in theory, but what can it actually do? Let's look at two of the most famous quantum algorithms that demonstrate the real-world, disruptive potential of this technology. First, there's Grover's algorithm, developed by Loaf Grover in 1996. Imagine you have a massive, completely unsorted database like a phone book with a billion names, but in no particular order. You need to find one specific name. A classical computer has no choice but to go through the list one by one. On average, it would have to check half the list 500 million entries to find the name. Grover's algorithm tackles this problem in a fundamentally quantum way. It uses superposition to look at all the names at once and then applies a clever series of operations that act like a quantum amplifier. With each step, the probability of the correct name is slightly increased, while the probabilities of all the wrong names are slightly decreased. It systematically amplifies the right answer out of the sea of possibilities. The result? It can find the name not in steps, but in roughly the square root of n steps. Even more famous and more threatening is Shor's algorithm, developed by Peter Shor in 1994. This is the algorithm that truly put quantum computing on the map for governments and security agencies. Its power lies in its ability to do one thing exceptionally well: find the prime factors of a very large number. This might sound like an obscure mathematical puzzle, but it's the very foundation of most of the cryptography that protects our digital world today. Your credit card transactions, secure emails, and private messages are all protected by encryption standards like RSA, which rely on the fact that it is incredibly difficult for classical computers to factor large numbers. A standard supercomputer might take trillions of years to crack a modern encryption key. Shor's algorithm, by exploiting the principles of quantum Fourier transforms, can do it in a matter of hours or days. It effectively renders our current standard of public key cryptography obsolete. While this poses a significant threat, it also opens the door to a new era of quantum-resistant cryptography. Shor's algorithm proved, without a doubt, that quantum computers weren't just a faster way of doing old things. They were a new form of computation that could solve problems previously thought to be impossible. We've journeyed through some incredibly complex ideas, from the nature of reality to world-changing algorithms. Keeping up with a field that is advancing this quickly is a monumental challenge for anyone, students, researchers, and even experts. How do you navigate this fire hose of information and turn it into something useful and understandable? This is where the next revolution in AI steps in to help us understand the quantum revolution. Let me introduce you to a new class of tools, exemplified by MGX Deep Research. Think about how you typically find information. You use a search engine, a single-agent tool. It gives you a list of links, and the hard work of reading, synthesizing, comparing, and structuring that information is left entirely up to you. MGX Deep Research operates on a completely different paradigm. It's not a single agent, it's a multi-agent system. Imagine hiring a dedicated team of AI specialists to tackle your question. One agent is the lead researcher. It scours the internet, academic papers, and databases to gather all the raw information. Another agent is the analyst. It takes this raw data, identifies key concepts, finds connections, and structures the findings into a coherent narrative. A third agent might be a coder, capable of taking theoretical concepts and building functional demos or code snippets to illustrate them. And a final agent could be the presenter, which takes the structured analysis and transforms it into a polished report, a slide deck, or an executive summary. This team-based, collaborative architecture allows it to go far beyond simple information retrieval. It supports the entire workflow of knowledge creation, from discovery and analysis to application and presentation. For a topic as deep and multifaceted as quantum computing, this is a game changer. It can help you build a comprehensive report, design a presentation, or even develop a learning tool, all while you guide the process at a high level. Let's make this concrete. Seeing is believing. Imagine you're a student trying to truly grasp the concepts of the Bloch sphere and quantum gates. Reading about them is one thing, but interacting with them is another. You could give MGX Deep Research a prompt like, develop a functional, interactive web-based qubit visualizer. It should display a 3D Bloch sphere. There should be buttons to apply an X gate and a Hadamard gate to the qubit. It should also show the corresponding probability chart for measuring a 0 or a 1, and this chart must update in real time as gates are applied. A single agent tool might give you some code snippets or links to tutorials. The MGX multi-agent system would get to work as a team. The researcher would gather information on the best JavaScript libraries for 3D graphics like 3.js and the mathematical formulas for the gate operations. The analyst would structure the project, what the user interface should look like, how the state of the qubit should be managed, and how the visuals should be linked to the underlying math. The coder agent would then write the HTML, CSS, and JavaScript code, implementing the 3D sphere, the gate logic, and the reactive probability chart. The presenter would package it all up into a clean, functional demo, complete with comments in the code explaining how it works. Within minutes, you would have a working tool. You could start with a qubit in the 0 state at the South Pole. You click the Hadamard button and watch it instantly jump to the equator, the probability chart showing a perfect 50/50th split. Then you click the X button and see it flip to the other side of the equator. This example shows how advanced AI systems are becoming accelerators for learning and experimentation. They bridge the gap between abstract theory and tangible, hands-on experience, allowing us to explore and innovate in complex fields like quantum computing faster than ever before. This powerful AI, capable of building complex applications on demand, doesn't just exist in a vacuum. It relies on a massive, sophisticated, and reliable infrastructure running silently behind the scenes. Let us pull back the curtain for a moment to appreciate the incredible engineering that makes tools like MGX possible, drawing insights from industry leaders like Superbase. Running a service that provides a unique, isolated environment for millions of users, whether it's a database or an AI workspace, is a colossal challenge. A key architectural principle they employ is the separation of storage and compute. Imagine a massive library. The storage is the physical building with all the bookshelves, holding all the information. The compute is the set of reading desks where people actually do their work. In the old model, every user got their own little library with a single desk inside. This was inefficient and hard to scale. The modern approach is to have one gigantic, centralized library storage and a flexible pool of reading desks compute that can be assigned to users as needed. This allows for incredible efficiency, easy backups, and the ability to instantly scale up the desks when demand is high without having to duplicate the entire library. But what happens if a part of this system fails? This is where concepts like failover through consensus come in. Instead of relying on a single master computer to manage everything, Modern systems use a group of servers that constantly talk to each other and vote on the correct state of the system. If the leader fails, the others can instantly hold an election and promote a new one, ensuring the service continues without interruption. It's a resilient, democratic approach to system management. Finally, how do you direct the millions of requests coming in every second to the right place? That's the job of a smart traffic orchestrator, a system we can call multigrass. It acts as an intelligent global load balancer, routing user traffic to the closest and healthiest data center, ensuring low latency and a smooth experience no matter where you are in the world. This invisible backbone scalable architecture, resilient failover systems, and intelligent traffic management is the unsung hero that enables the AI revolution and, in turn, helps us make sense of the quantum revolution. We've traveled an immense distance today. We started with a single spinning coin and ended with the global infrastructure that powers the future of computation. The world of quantum computing is no longer a distant dream. It is a rapidly maturing field, and though we are still in its early days, its impact is already beginning to ripple through critical domains. In cryptography, it presents both a challenge and an opportunity, forcing us to build a new generation of quantum-safe security. In chemistry and materials science, quantum computers promise to simulate molecules with perfect accuracy, allowing us to design revolutionary new drugs, catalysts, and energy-efficient materials. In finance and optimization, they could solve complex logistical problems that are currently intractable, optimizing everything from global supply chains to investment portfolios. But beyond these practical applications, the journey into the quantum world offers us something more profound, a new way of thinking. A quantum mindset in your own life. How often do you collapse into a definite 0 or 1 too quickly? The principle of superposition teaches us to embrace ambiguity and hold multiple possibilities in our minds at once, to explore the full spectrum of potential before making a decision. The spooky action of entanglement reminds us of the profound interconnectedness of our world. Our actions and intentions can have non-local effects, creating synergy and coordinated outcomes in ways we might not always see. It's a powerful metaphor for teamwork and empathy. And interference shows us how small, focused efforts, when aligned, can build on each other constructively to create massive results, while scattered, conflicting efforts can cancel each other out into nothing. It's a lesson in the power of focus and alignment. The road ahead is long and filled with challenges, from building stable hardware to developing new algorithms. But the convergence of these three mighty forces, the deep reality of quantum physics, the scaling power of modern infrastructure, and the clarifying lens of artificial intelligence, is creating a perfect storm of innovation that will define the 21st century. So I leave you with a few questions to ponder. What problem, big or small, would you want to solve with the power of a quantum computer? And how can you apply the quantum mindset of possibility, connection, and focused interference to the challenges and opportunities in your own life? Thank you for joining me on this incredible journey. Stay curious, stay healthy, and never stop questioning the nature of your reality. If you found this journey as fascinating as I did, and you want to explore more frontiers of science and technology, please show your support by hitting that like button. And be sure to subscribe to our channel and turn on notifications so you don't miss our next adventure. We'll see you next time.